Swayam Prabha. Digital India. Educated India.
So today's discussion topic is probability. The first question that comes to our mind is, what is the need of knowing probability? Now what happens is that many a times we have to draw a conclusion about the population when only a part of the population has been examined. That is, only a sample of the population is actually examined, but we need to estimate some parameters of the populations. So this is what happens many a times, because the entire population sometimes is difficult to examine. In such situations, there is some amount of uncertainty about the conclusion that we will draw based on a sample that we draw from the population and examine it. Since we are not examining the entire population, but only a sample part is examined, therefore an uncertainty is always involved in whatever decision we take. So uncertainty is there about the conclusion that we draw based on sample data. Now, a measure of degree of this uncertainty is provided by probability. That's why the probability theories have been developed, and we want to express the extent of uncertainty about the conclusion that we will draw based on the sample data. Now we have to discuss this thing, the non-deterministic experiments, and what is the outcome of those experiments, and what do we understand by sample space, and what do we understand by an event. These are very, very important part, we can say, of the statistics. That is, we should be familiar with these terminologies. Now, an experiment could be, let us say, toss a dice and observe the number that shows on the top. So let us say we toss a dice and observe the number that shows on the top. In this case, the possible outcomes are as shown in the second column of the table, that is 1, 2, 3, 4, 5 and 6. These are the possible outcomes, because a dice has 6 faces and a number is there on each face. So outcomes are either 1 or 2 or 3 or 4 or 5 or 6, and hence the sample space is written as S1 for the experiment 1, which is 1, 2, 3, 4, 5, 6. These are the possible outcomes. So possible outcomes are basically my sample space. And then an event for this experiment is, let us say, an even number that occurs. So if I describe the event as an even number, then the event E1 represented in this case basically means it is 2, 4 or 6, because they are the even number. So in this experiment, these are my outcomes. Outcomes are basically sample space and an even number, or somebody can say odd number, that could be an event. So the event has to be described. What we want, what information we want from this experiment. So that we can define the event and we write. So in this case, an event number occurs. If this is the event that we describe, then E1 is going to be 2, 4, or 6. That is, an event is a set of possible outcomes. So an event is a subset of the sample space. So you see, the sample space is 1, 2, 3, 4, 5, 6. Out of that, 2, 4, 6 is a subset of this set. So the event is always a subset of the sample space. Any individual outcome could be also an event. So any single outcome can also be described as an event. That is, if I say the event is to observe 1 on the face, so that could be an event. So in that case, E1 becomes only 1. And the other thing is the whole sample space is also could be an event. So event could be only one outcome, it could be all the outcomes, or it could be a subset of the outcome. We will go for another experiment just to get a clear idea about experiment, outcome, sample space, and event. Toss a coin 4 times and count number of heads. So think that you are tossing a coin 4 times and you are counting number of heads that you can see. Now the possible outcomes could be either 0 or 1, 2, 3, 4, because it may so happen that in all the 4 tosses you never saw head. In that case, it will be 0. Or you may find that you saw head only once, or maybe twice, or maybe 3, or maybe all the 4 tosses resulted in head. In that case, it will be 4. So the possible outcomes are 0, 1, 2, 3, and 4. And therefore, the sample space for this experiment is going to be 0, 1, 2, 3, 4. And I can describe an event that 2 heads to occur. That means event in this case for experiment number 2 is going to be only 2. The number of heads that can be observed could be either 0 or 1 or 2 or 3 or 4. And if the event is described that 2 heads will be observed when the coin is tossed 4 times, and therefore the event will be E2 in this case is going to be 2. Another experiment, counting defective items produced in a production line over 24 hours. Over 24 hours, we keep and watch and find out how many defective items have been produced. So defective item, let us say D, could be 0, 1, 2, 3, 4, it could be up to n. N is whatever is the value of n. N is the maximum defects produced. So these are the possible outcomes. The sample space is exactly same. And I can describe an event like more than 2 defectives. So the event E3 is going to be defects D to be greater than 2. It could be 2 or 3 or 4 or 5, whatever it is. So that is how the event can be described. Another example, abrasion cycle steel failure of a fabric. You all know that many a times we test the abrasion resistance of fabrics. So how many cycles of abrasion is required till the fabric fails? So that number, suppose we are recording. So this possible outcome could be C has to be more than or equal to 0. And the sample space is going to be C greater than or equal to 0. At the same time, if I define an event like failure occurs less than 5,000 cycles, in that case, the event will be described as E4. In this case, C is less than 5,000. Or sometimes it may go beyond 5,000 also, it can go 6,000, 7,000. But if we are interested that failure occurs at less than 5,000 cycles. So that could be an event. And the next one could be tensile strength of yarn. So similarly, tensile strength represented by T is greater than or equal to 0. Sample space is going to be same, T given T greater than or equal to 0. And the event could be strength of the yarn greater than 300 gram force. So we should write the event as E5 T oblique T greater than or equal to 300. So that could be the event. So that is how the experiment, outcome, sample space, and events can be described. Next we go to another important aspects, that is called Venn diagram. So this is one Venn diagram which is shown here, but we'll come to more about it now. Now Venn diagram represents relationship between events, and sample space is usually represented by a rectangle like this rectangle we show, and whatever is there within the rectangle we call this is my sample space, and we write the letter S representing the sample space within the boundary of the rectangle. Event is usually represented by a circle. So within this sample space there is a circle, and we write the letter A, where A is the event. In this diagram and the previous one more, what we write it here is A bar, which is known as complement of A. That the rectangle represents the sample space. Any event within this is represented by the circle, and suppose in this case the event is called event A. And if we leave the event A, then whatever is left, that part of the sample space, that will be known as complement of A. That means rest of the area A does not exist. So A is here, and A bar or A complement means that area of the rectangle, in this case, where A does not exist. We call it complement of A. That is, A is not there. The event A is not there. Here there are quite a few representations of the event sample space. Some examples are given here, like these are basically a part of Venn diagram is also taught in the case of set theory. So those who have already studied set theory, they already know about it, that In this case, let us say this circle A and B, and if we want to say the set A representing in this case the event A, so this green circle is representing the event A. Now the complement of A is shown in this next diagram, this diagram. Complement of A means that part of the rectangle where A does not exist. So you look at only the green color, that is the area where A is not there in this particular second diagram, the second rectangle. So that is that area basically representing the complement of A. Next, in the next diagram here, A and B are disjoint sets. So there is a event A, there is a event B. So this is basically A and this is basically B, but these two circles are not overlapping each other. So they are independent. So it is a disjointed set, or we can say these are independent, mutually exclusive events. We will discuss about them, not independent, mutually exclusive events. That is, there is no common area between A and B. So at times the event may be such that there is no common area between them. So we say event A and event B, they are separate from each other. We will see some examples later on. In this case, see, B exists within A. That means B is a subset of A. B is the subset of A in this case. Then in this diagram, what we see, A and B, and you see, look at this green area. Green area is the common area. So the green area basically means in this case that it is part of A and it is part of B also, because A is here also, B is also here also. That is what we call the intersection between A and B. So it is written as A intersection B. This is the area which is A intersection B, where A also exists and B also exists. And the last one in this case is A union B. What we see, whatever is the green part we see, that means the total area of the two circles. The area from here going there, then going here and coming back here. This entire area is called A union B. This is how now we can represent the events, because such kind of diagram can, if we, it helps us to basically solve the problems and to visualize the problems also. So they will be very helpful while we try to understand the problems related to the probabilities. But basically this part is basically a kind of set theory. So those who are already familiar with set theory, they will be able to understand it very fast. The next is the definition of probability. One is the classical concept. What is that? If there are n equally likely possibilities of which one must occur and S are regarded as favorable or as success, then the probability of success is what? It will be S by small n. This is the classical concept of probability. So if there are n equally likely possibilities, so all the possibilities has to be equally likely. That is very, very important word. Of which one must occur and S are regarded as favorable. That is, they are regarded as success. then the probability of success is defined as P, which is S by small n, or S represents success, and n is the number of possibilities that exists. Example, suppose a dice is thrown, the events A occurs if and only if a number larger than 4 shows. So I am defining an event by saying that the event means the number has to be greater than 4. So what is the probability of A of this event? So A is larger than 4. What does it mean? A in this case is going to be 5 and 6. 4 is not included. All outcomes are equally likely when a dice is thrown. And when dice is thrown, the sample space is 1, 2, 3, 4, 5, 6. And all of them are equally likely. So all outcomes are equally likely. Therefore, P of A in this case is going to be S by N, where 1 is A, 5 can happen. What is the probability of 5 is going to occur? 1 upon 6. And then 6 also will come, and for this there will be another 1 upon 6. So it will be 2 by 6, and therefore it will be 1 upon 3. That is going to be the probability of A. So probability of getting 5 is 1 upon 6, probability of getting 6 is also 1 upon 6, and we are adding these two. That makes it 2 by 6 or 1/3. The other probability interpretation is frequency interpretation of probability. Suppose a trial is repeated n times and an event occurs f times. Then the probability A will occur in any future trial can be given by PA is equal to f by n, where A is the number of times A occurs out of n trials that we take. So relative frequencies are the estimate of probability. Now what is relative frequency? We'll come to that now. Look at this table now. The table shows that first column is number of end breaks per hour. So on a spinning machine, we are counting the number of breaks per hour. And this is the data we get. Column number 2 gives number of hours, the frequency. So 0 break was 28 was the frequency, 1 break 40 hours there was no break, the frequency is 40. Break number 2, this thing happened 20 times, so therefore 20 hours. 3 is 8, 4 is 3. So this data suppose is there, this table is given here. From here we can calculate what is the relative frequency. So what we do first? We add all of them, these frequencies. Total is 100. 28 plus 40 plus 20 plus 8 plus 3 plus 1, that gives 100. And then the relative frequency is frequency divided by total frequency. Individual frequency divided by total frequency, that gives the relative frequency. So 28 by 100 is 0.28, 40 by 100 is 0.40, 20 by 100 is 0.20, 8 by 100 0.08. So these are becomes my relative frequencies. Relative frequencies are also known as probability. So probability of getting 0 break, I can say 0.28. probability of getting 3 break is 0.08. So relative frequencies are the estimate of probabilities that a given number of n breaks will occur in future. So if I say probability of 2 n break, that is PA is going to be 2, exactly 2. So the value will be this one. For 2, this is the corresponding value. So it will write PA is going to be 2 is 0.2. So these are the two ways that probabilities can be determined. So relative frequency, as I said, frequency by the total frequency. That is what is relative frequency. Now the scale of probability, that what could be the maximum and what could be the minimum value or probability. Consider two extreme cases. First, suppose that the event A is impossible. Since A will never occur, therefore F is going to be equal to 0. Some event is suppose impossible. Then obviously the frequency of that event is going to be always 0. So F is 0. If that is true, then P for an impossible event is going to be 0, because the probability is F by n. If F is 0, numerator is 0, therefore the probability is going to be 0. Another one is the event, suppose, is certain to happen. Here it is the event. The event is certain to happen in any trial. Then in every trial E will occur so that F is equal to n. That is the event. Event is, let us say we're writing event as E in this case. So if event is, same event will differently occur, then F is going to be n, and in that case P for a certain event which will definitely occur is going to be F by n is n by n equal to 1. Like say the event that sun will rise tomorrow. What is the probability of the sun will rise tomorrow? It is always 1. Why it will 1? Because we know that event will must occur. Even if I observe for 100 days consecutively, every day we will find the sun is rising, and therefore such kind of phenomena where we are certain that the event will definitely occur, F is going to be n, and therefore the probability of such kind of event is going to be 1. That means the scale is from 0 to 1. Go to the next one now. Axioms of probabilities. Axiom 1 is the probability of an event will be always lying between 0 and 1. Next, P of the entire sample space is always going to be 1. That sum of the probabilities is always going to be 1. And axiom 3 is the addition rule of the simple form. If the events A and B are mutually exclusives in S, that is in the sample space, then P A or B will be PA plus PB. We'll see how and why does it happen, but this is something very important, that is the word mutually exclusive. If the events are mutually exclusive, that is, what does it mean? And when one of them occurs, the other cannot occur. If I toss a coin, either head will occur or tail will occur. Head and tail cannot occur simultaneously in a given flip. Therefore, these two outcomes, head and tail, are mutually exclusive. And if I represent them by this diagram, event A and event B, within the sample space S, there is no common area between them. They are mutually exclusive. That means when A is happening, B is not there. Where B is there, A is not there. Then P A union B will be how much? This area and the area of B. You can assume that as if the properties basically mean this area of circle A and area of circle B. So the area of these two union stands for addition. So PA union B means PA plus PB. So these are the notations how we write. P stands for probability. Then we write within bracket A or B, or we write it as A union B. This union in this U indicates union, means addition. In words, we can think A or B. So it will be PA plus PB. Now we will take an example of this. The table below, so what is the table? Table is here. The table below shows the end breaks and their frequencies. This table we are familiar with. I have already shown the table previously. And their frequencies. Calculate the probability of less than 2 breaks. The breaks will be less than 2. So here number of breaks, frequency is there, and we calculated already the relative frequencies, which are basically the individual probabilities. So less than 2 breaks basically mean in this case because they are independent event. So probability of no end break and probability of one break. That means we are interested in this and this together. So they will be 0.25 plus 0.440, and therefore the answer is 0.65 because it is less than 2. So we cannot include 2. It has to be 0 and 1, not 2. So the answer is 0.65. So these two end break, one end break or two end break or zero end break, they cannot really occur simultaneously in a given hour. In a given hour, either you will have figure 0 break or 1 or 2 or 3 or 4. So all these events are basically independent of each other. Or we can say they are mutually exclusive, not independent, they are mutually exclusive. That is the term we have to use, because if we get in a given hour, if we watch, if there is a 0 break, same time we cannot obviously cannot have 1, 2, 3, 4 breaks. The next hour we may have 1 break, but in that power hour, so our 1 hour duration is the slot time. In that slot of time, we can only expect either 1 or 2 or 3 or 4 or 5. So they are all basically mutually exclusive. Now, generalization of addition rule. From the same experiment, the simple form of addition rule is concerned with mutually exclusive events. That is, PA union B is PA plus PB. This is true for simple form addition when the events are mutually exclusive. However, there are many situations when this is not true. Let us say we describe event A as fewer than 2 end breaks, and event B has end breaks between 1 and 4. In these cases, these two events, you will find they are not really mutually exclusive. PA fewer than 2, we have already calculated the value is 0.65. But what is PB? End breaks between 1 and 4. That means from here to there, all them to be added. So 0.4 plus 0.2 plus 0.1 plus 0.04, 0.74. Now PA and PB are not mutually exclusive. Therefore, PA union B equal to PA plus PB. If we do it this way, the value is coming get 1.39. This is something which is not true, because we know that the answer cannot be more than 1. Probability cannot be more than 1. So this rule, simple rule of addition, will not work. In this case, what we need to do, event A and B are not mutually exclusive, because within event B, actually event A is also included. This data 0.40, which belongs to event A, is also part of event B. So that means this is not, these two events, in the way we have described the event, they are not mutually exclusive. That is it. So therefore, this way of solving the problem is wrong. So events are mutually exclusive when both cannot occur simultaneously. Now what should be the right answer in this case? If one break occur in an hour, then it can belong to both A and B. As I said, this particular event, this data, it belongs to both A and B. So that has been, if I just add PA and PB, that means this gets counted twice. While counting while finding out PA, we add these two. While finding out PB, we add it from here to there. That means this one event that breaks one break event was added, that probability was added twice, and hence it was coming wrong. So the probability of occurrence of one break must be subtracted, which was included here, also included here. Two times is getting included. So what we'll do, we'll subtract this. So in this case, PA union B is going to be PA plus PB minus PA intersection B. This notation basically means that A and B both are happening together. So that is 0.40. So it will be 0.65, 0.74 minus 0.40, 0.99. So this is, in this case, the event A and B are represented here. So A intersection is B is this area, where, and this intersection area is how much? Is actually 0.4. And therefore, if I want to find out the total area, PA union B, so it will be PA plus PB minus, I have to subtract the intersection where PA and B are occurring simultaneously. And if we subtract this, we get the right answer. That means PA union B will be PA plus PB minus PA and B, or we call it PA intersection B. A and B basically meaning both of them are occurring simultaneously. So this is the general rule. If they are mutually exclusive, then P intersection B, this will not be there when the events are mutually exclusive. Okay. Now we can have 3 events, 4 events also possible. So just let us say we are going up to 3 events. A, B, C are shown as 3 different circles representing 3 different events, and you see so many common area between the 3 events A, B, C. They are all overlapping. Within that, there is one area which is a part as shown by this hatched line. This area is actually part of A, also part of B, also part of C. This is part of the pink circle, it is a part of the green circle, it is also part of the C, that is the blue circle. So this is the common area or intersection area of A, B, C together. In this case, probability of A or B or C, we write it P within bracket A union B union C. That means we are interested to know this entire area from here to there, this part as it. This we can find out the probability of P, A, B and C, A union B into C is P of A, P of B, P of C minus P A intersection B minus P A intersection C minus P B intersection C plus P A intersection B A B C. Now this can be proved also. Mathematically this can be proved as well, but we are not going into that, but this can be easily proved. So if I say P A union B union C is what? P A plus P B plus P C minus P A intersection B, A intersection C and B intersection C, because these common areas of A, B, B, C and AC, they are getting counted every time I take A or B or C. So we have to subtract that area or that probabilities in this case. And finally, we have to add this. That will give you the probability of A or B or C together, or A, B, C together. If A is an event in S, then what does P A bar means? A bar means A complement. Complement basically means where A does not exist. So if the S is here, so A is this circle, rest of the part is PA bar or PA complement. So PA complement, if I want to find out, that is probability of complement of A will be 1 minus PA, because the total probability of PS is actually 1. S includes the entire part. So PA bar or PA complement is 1 minus PA. Now we will solve a problem. Example, a piece of equipment functions only if 3 components A, B, C are all working together. So there's equipment where there are 3 components A, B, C. When all of them function, the equipment functions. The probability that A, B and C will fail are 5%, 15% and 10% respectively. What is the probability that the equipment will fail before the end of the year? This is what we want to know. What is the probability that equipment will fail? The equipment has 3 parts and these 3 parts have different probabilities of failure. How to go about it? The solution will be the equipment will fail if either A fails or B fails or C fails. It is not that all A, B, C should fail together. Even if one of them fails, the equipment will fail, because all of them have to work together, then only it will work. So you know that P A union B union C is PA plus PB plus PC. This formula was given earlier. So here, this is what we need to use. So how much is PA? Is 5%. So 5% basically means probability is going to be 0.05. 15% PB is going to be 0.15, and 10% means PC is going to be 0.1. So these are the probabilities of A is going to not going to work 0.05, B not going to work 0.15, C not going to work is 0.1. Since then, the failure of the component are independent of each other. Now we have to find out, because they are independent components, so there is no link between A and B. It's not that A fails means automatically B fails. It may so happen that A has failed but B may not have failed, or C may not have failed. So they are not dependent on each other, that failure. So PA intersection B is going to be how much in this case? Because A and B are independent events, or there, and therefore PA intersection is B is going to be PA into PB, which is going to be 0.05 into 0.15, that is 0.0075. PB intersection C is going to be similarly PB into PC. So it will be 0.15 into 0.1, 0.015. PA intersection C is going to be PA into PC. So PA is known, PC is also known. We substitute those values and get these figures. And now PA intersection B intersection C is going to be how much? Because they are independent events, so it will be PA into PB into PC. So the value is going to be 0.00075, and therefore P A union B union C the probability that equipment will fail means either A fail or B fail or C fail. So when this either or comes, then we write it by this notation A union B union C. So the formula was there. We substitute these values here and we will get the answer now. The answer is coming to be 0.27325. In percentage terms, it will be 27%. You multiply it by 100. That means the probability that equipment will fail before the end of the year is 27%.